All right, this is our problem. So we've got the car racing down the back alley. The acceleration is 1/4 of a meter per second squared as it moves along. And so that's good for me to just circle that this is, oops, over here. This is our value, 1/4 meters per second squared as it moves along, and that its mass is this. So our mass is known and our acceleration is known. So there's several things that we can get just from that. The weight of the remote control car would come from the Fg equals m times g expression. Since we know the mass is 3.5, we're going to take that and multiply it by 9.8. Sometimes we'll shortcut and do 10, but we should probably stick to 9.8 for a scenario like this. So that would be equal to 3.5 times 9.8. That's throwing me off. Okay, so what is that calculated into? Anybody with a calculator? What do you need? 35 times, or 3.5 times 9.8. Should be just under 35.
It's 34.3.
34.3. That's really hard to read, but we're going to go with it. So 34.3 is the number of newtons is worth writing, but that's wow. Newtons. Okay, 34.3 newtons is our weight on the car, and that's how much the force of gravity is pulling down on the car is important to keep in mind for its weight. And so the net force that's acting on the car is the next thing that this problem has to calculate. The net force you can always get back from information that's given if they give you the mass and the acceleration. So we know that net force is equal to mass times acceleration, and so if we're dealing with net force is equal to mass times acceleration, we have a mass and we have an acceleration. So that would be equal to 3.5 times the 0.25,
It's 0.875.
which is 0.875.
What's the unit for that?
And that is a force, so it's back to another newtons. I gotta fix that calibration. But the next question is, are the gravitational force and normal force acting on the car in equilibrium? And for that, I think I would really want to have a free body diagram to really process what that means. So I'm going to scroll this up, and we can think about what are the forces that must be in play on the car. Here we've got our car, and we're going to have gravity and normal, which I think are going to be in equilibrium. Then we can go this way and this way. If we notice that our car is accelerating in that direction, I usually use a double arrow just to denote acceleration. They're going that way. That means that this, which is my force applied, and then here's my force of gravity, and this should be the normal force, and this should be my frictional force over here on the left. Those four forces are what are in play on this car. The normal and gravity, just like by intuition, I'm guessing that the car is driving along the road, not hopping up and down on the road. So in terms of its motion, it should be just a horizontal motion. So the vertical has no motion in it directly. So I'm going to say that since there's no motion in the vertical dimension for the car, it's driving along the road, then it's going to be in equilibrium, right? No motion means it's not accelerating either, and so if a zero acceleration is true, then my net force in the y must be true. So the normal and gravity have to cancel out. And that's commonly true for things that are sitting on the ground or along a surface, like the microphone on the table. Its gravity and its normal are balanced. And so that's a common scenario that people try and make an always global statement, which you shouldn't do either, but it's a really common scenario. So the next statement is asked, so then it does ask us to explain, so an important question, because it's going to ask us about friction next, is what is the amount of normal force? And so in order to do that, I want to think about what's the net force in the y, and that's going to equal 0, and that comes from the normal force plus the force of gravity. And so since I know the force of gravity is downward 34.3, then the normal force must be up 34.3, right? So I can say 0 equals the normal force plus minus 34.3. That was practice. And so the normal force must be equal to positive 34.3 in order to balance that out, right? Since we know it's a zero equilibrium for the y-axis, and we know that gravity is pulling down with 34.3 newtons of force, the normal has to be pushing the other direction with that much. We all okay?
Mhm.
Okay, cool. The car has a frictional force of 15 newtons, and what's the observed coefficient of friction? This equation often trips people up just because it's sort of different from the rest of the nature of it. And it's that the force of friction, and there's static friction and kinetic friction that we can suss out and do more detailed things with. But let me give you the short version, is it's not on the tests. It's not distinguished on the tests, other than maybe in the multiple choice. So you treat it with the same equation both ways. The force of friction is equal to the coefficient of friction, and so it's this goofy Greek letter mu times the normal force. And these are always treated as absolute values for you guys, because really this is a dot product or a cross product. It's some matrix math that we don't really get into if you want to go in the real mechanisms of how and why this works. But always absolute value are your numbers that you put in here. So the normal force in this case is 34.3. The force of friction, it says in the problem, is 15, and that equals the coefficient that we need to solve for. And so in order to solve for that, all we need to do is divide both sides by 34.3. So this divided by 34.3, and it's going to be like 0.4 something. U equals 0. So do it. You're good.
It's 34.3 divided by what?
15 divided by 34.3.
0.4373.
Okay, cool. 0.4373. We're good, right? It's good to be how it looks. So that is our coefficient of friction. This is a unitless value, and there's no, so it's unitless, and it's just a ratio for how much friction do you get for a given amount of normal force. For a lot of objects, it's between 0 and 1, and it's unitless. So if you're trying to figure out a coefficient of friction, if it's outside of that range, a little red flag should go off. They're never negative, because that means that it would slip more than it sticks. And it's weird, yeah, don't try and think about the implications of that too much, Alexi. I saw the furrowed brow. The shoes, however, are commonly above 1 because they're trying to stick to the ground. So if you were to take a shoe and put it on a ramp and hold the ramp up at an angle and do some backwards math to try and figure out its coefficient of friction, they're often like 1.4, 1.5. Because you want to have good traction. And so tires and shoes and some of those things that are designed to stick are outside of the 0 to 1 range. But most stuff is 0 to 1. So this question, what force must the motor be applying based on this motion? Question E comes back to our assertion. So for this problem, we need to think about what are the things that we can assert based on this free body diagram. We made an assertion in the Y, but we didn't do one in the X. Let's see if I can erase efficiently up here. Oh, I can't. Okay, great. So we'll do that, and then come back to the marker. This is in the Y. We can make another assertion in the X. So our net force in the, that looks like a, this is the X one. That's the X one. In the X, our net force is where our acceleration is. So we're going to make another statement, but we know it's not a 0 because it is accelerating horizontally. So I'll say that this is equal to an M and an A. And that's going to come from our two horizontal forces in this problem, which is the force of acceleration to the right and then the force of friction to the left. Since I know that this one is going to be negative 15, I'm just going to add it. And then this one is what we're really trying to look for. So we're trying to solve for what's our applied force. So when we do this, we've got our force of friction plus our force that's applied. So that's going to be our assertion in the X dimension. We know that that's the dimension that gives us our acceleration, and those are the two forces that are in play. So if we knew that from up there in C, we can apply it down here in E. So what force must the motor be applying based on this motion? We know that the MA equals force of friction, works better with lowercase, force applied. That's our statement that we could work with to really solve this problem. Since we know the mass, we know the acceleration, and we know the force of friction, in this part of our assertion, we know everything except for one of the pieces. So we can say that this is 3.5 times 0.25, and then that equals negative 15 plus the force applied that we don't know. So we could take this and solve for the applied force. So this was some number that we had come up with before. The net force in the X was 0.875. So 3.5 times that is 0.875 equals negative 15. That's a bad looking 5. Plus the force applied. So I'm going to add 15 to both sides. So plus 15. So my applied force must be, I'm going to take this right here and just write it over there. 15 plus 875. There's a plus there. There. That's where the decimal goes. So that gives us our net force, or the force that must be applied. You'll notice it's bigger than the friction, right? There's a tug of war between the two horizontal forces. The pushing force has to be more than the friction force in order for us to observe this acceleration of 0.25. It's a tug of war, and the applied force has to be bigger than the applied force has to be bigger than the frictional force by the amount that leaves you with the net force. And then explain the relationship between net force, applied force, and frictional force from this example, which is what I just did perfectly. I'm going to stop this video because it's